Have you ever wondered what kind of engine can survive the vacuum of space, resist temperatures hotter than molten lava, and still deliver enough power to launch 400 tons of steel into orbit? Imagine standing at the edge of human possibility, watching as a pillar of fire lifts hundreds of tons of machinery off the planet's surface and into the silent void above. At the heart of this awe-inspiring spectacle lies the space-grade rocket engine, an achievement so extraordinary that it rewrites the rules of engineering with every launch. These engines are not just powerful, they are masterpieces of survival and endurance, designed to operate in the harshest environments ever faced by any human-made machine. The story of a rocket engine begins long before the countdown. It starts in the heart of specialized aerospace foundries, where teams of metallurgists and engineers work in tandem to create alloys that can withstand unimaginable stress. Ordinary steel or aluminum would buckle under the extremes of rocket flight, so scientists blend rare metals like titanium, nickel, and niobium to create superalloys. These are forged in furnaces hotter than volcanoes, squeezed under pressures approaching those found at the center of the Earth. Only the purest, most resilient metals make the cut. Each batch meticulously tested for flaws, invisible to the naked eye. But even the strongest metal cannot survive the inside of a rocket engine unaided. Temperatures in the combustion chamber soar to more than 3,300 degrees Fahrenheit, hotter than molten lava and enough to vaporize most materials instantly. To tame this inferno, engineers employ a marvel of microscale precision, regenerative cooling. Here, the engine's cryogenic fuel, chilled to hundreds of degrees below zero, courses through an intricate web of microscopic channels etched directly into the chamber walls. As the fuel absorbs heat, it prevents the metal from melting, creating a delicate balance between fire and ice that keeps the engine alive for just long enough to do its job. Crafting these cooling channels is a feat in itself. Advanced robotic arms, guided by laser and computer vision, carve grooves thinner than a human hair into the engine's core. Each groove must be flawless. One defect, and the entire engine could fail catastrophically. The engines are assembled in sterile, clean rooms, where a single speck of dust could compromise the integrity of the final product. Every bolt is torqued to exact specifications, every seal tested and retested. Once assembled, the real test begins. The engine is bolted down to massive test stands, designed to withstand the roar and fury of a simulated launch. When fired, the noise is so intense that it can shatter windows a mile away. As the engine spews flame, a small army of engineers monitors its every heartbeat, using high-speed cameras, thermal sensors, and AI-powered diagnostics to catch even the slightest anomaly. The heat, the vibration, the stress, all are measured in real time, and any deviation from perfection is scrutinized. Only after surviving these brutal trials is the engine deemed worthy of flight. It is then painstakingly cleaned, sealed in anti-static containers, and transported, often by specially chartered aircraft, to remote launch facilities. There, it is integrated with the rocket, becoming the muscle that will hurl satellites, scientific instruments, and even humans beyond the confines of Earth. What makes these engines special is not just their raw power, but the orchestration of chaos they represent. Every second of flight is a triumph over physics, a furious, controlled explosion made docile by human ingenuity. In the relentless quest to explore the stars, the space-grade rocket engine stands as a testament to what humanity can achieve when we refuse to accept limits. This is not just engineering. It is an art form sculpted in metal and fire, hurtling us ever closer to the unknown.